Acids and bases are two classes of compounds that are important to think about, particularly when we start talking about water quality and also what's in our rain. Acids can be defined as those substances that release hydrogen ion, H+. As your book told you, H+ is often called a proton. So if you see a proton, that's exactly what they're talking about. Note again that this is an ion. Ions are missing electrons, so the H+ is a hydrogen ion minus its one electron. And what they're doing in solution is forming what's called hydronium ion. Again, as your book pointed out, H+ isn't going to stick around by itself. What it does is it attaches itself to a water and makes this hydronium ion. You can tell an acid because it tastes sour. You're familiar with this quite a bit in your kitchen. You go taste lemon juice, you go taste orange juice, those sorts of things. You know that they're acidic because they have that sour taste. I wouldn't recommend this for things outside of your kitchen, right? Don't go tasting your household bleach just to see if it's an acid or not. Bad idea. Secondly, the thing about acids that's going to be interesting to us is that they're able to dissolve things like metals or carbonates like limestone. We'll talk about that later, but that becomes really interesting to understand why rust happens and also why our lakes in this area that are limestone bed are a little bit better at reducing pH change than other lakes. Our second class of compounds is bases, and the way we like to abbreviate those is by using a B with a colon, right? Those colon dots are actually lone pairs, right? We think about bases as having lone pairs. Acids have HAs, they have H's that they lose. Bases don't have any H's to lose. What happens with a base is that they produce hydroxide or OH- in aqueous solution. Acids release H+, bases release OH-. And bases, you'll notice, feel soapy or slippery. Again, I wouldn't recommend necessarily going to do this. It's not the best thing in the world. In fact, the reason bases feel soapy or slippery is because they're actually taking your skin and converting the proteins in your skin to soap. So let's take a look at some of these chemical equations for acids and bases and understand why acids break up to release H's and bases break up to release OH-. So if we look at an acid, and we know that it breaks up to release H+, we could think of a compound like HNO3. This is called nitric acid, right? It's got the nitrate ion and it's got a hydrogen in front of it, right? How do we know it's an acid? Well, it's got that hydrogen up front. It will always have a hydrogen up front if it's an acid. And all it does is it breaks up into its ions. We end up with an H+, right? We always get a proton. And the phase label is AQ, or aqueous. The other ion is just what's left over. It's NO3-, aqueous. That's how they break up in solution to release H+. Let's try another one. This is H3PO4, right? It's got 3 hydrogens up front, so this one actually has 3 hydrogens to lose. That's okay. We actually only lose 1 hydrogen at once, so there'll always be 1 H+, and it will always be AQ, aqueous, and then whatever's left. So I took 1 hydrogen off the front of that H3PO4. Now I have H2PO4. And it's got to be a negative. Let's take a look. Over here, there's 0 charge. And then over here, we have +1 plus -1 equals 0. That's good. We should have 0 on both sides. So you want to make sure that your charges, your plus and your minus, really do add up. Alright, let's take a look at bases on the flip side here. Bases break up to release OH-, right? You can see that there's definitely a hydroxide here, can't you? So we end up with Na+, and that's aqueous, and OH-, aqueous. Next up, let's try another one. BaOH2. That 2 should be a subscript, so this should actually be BaOH2 solid. And again, it just breaks up. Now, if you go and take a look at the periodic table, you're going to notice that barium forms a 2+ ion, and it still will, right? That's barium 2+. Now take a look here. If I look at that formula for the hydroxide, the barium hydroxide, aren't there 2 of them? So I have 2 OH-, and they're still AQ, right? All the phases on these are going to be aqueous AQ. let's check out our charges. Do they add up? I've got a 2 plus for the barium, and then I've got 2 1 minuses. So it's plus 2 and negative 2 makes 0, and it was 0 on this side. Excellent, we're doing just fine. You want to make sure that you can just break up an acid and a base. Can you break up an acid like HNO3 into H plus and NO3 minus? Can you break up a base like BaOH2 into its constituent ions? You want to be able to just divide these guys in half and figure out how they break up and what you get. And remember, with acids, it's very important, 1 H plus at a time. No more, no less. There's one exception, and I'll just make a little bit more room here. I told you that bases break up to release OH minus, that you could recognize a base like NaOH, like barium hydroxide, because there was an OH minus at the back end. The exception is NH3, ammonia. Ammonia is a base. Your book goes through why it's a base and how it's a base, right? It actually reacts with water and takes away a hydrogen from water to leave a hydroxide. I just want you to know that it is a base. I'm not requiring you to know chemical equations for why. So moving on, let's take a look at some of these compounds here, and we want to know whether these chemicals are acids or bases or neither. And if they are acids or bases, write a chemical equation for what happens in water, so break them up. So the first one, NaCl. Okay, let's take a look at this guy. If it were an acid, it would have an H to lose. I don't have one. If it were a base, it would have an OH minus to lose. It doesn't. So this must be neither. What about our next one, HClO? Can you see the H right up front? That's got to be an acid. So I have HClO, and what it does is it breaks up into H plus, and we'll go ahead and make it start as a liquid, aqueous, plus ClO minus aqueous. Let's take a look at one more. LiOH. If I divide this in half here, do you see the OH minus at the back? So I must have LiOH. These all start out as solids. Bases start out as solids. You have Li plus aqueous plus OH minus aqueous. And one more. The last one to look at is NO2. And we do the same thing. I don't see any H pluses. I don't see any OH minuses. And so the answer is neither. But we're going to put an asterisk on that. We're going to come back to that in just a moment and understand that actually NO2 has the possibility, the capability to become an acid. So the question is, what does it mean to be acidic or to be basic or even to be neutral? So solutions can be neither acidic nor basic. And what we need for that is a way of quantifying, and that way of quantifying is pH. And what the pH measures is the H plus concentration in solution. Whenever you see those square brackets, that means molarity. So when you have lots of H plus, that's what's called an acidic solution, right? The definition of an acidic solution is that there's lots of H plus in it. Very little, so if the H plus is very low, means basic solution. That means lots of OH minus. Last, you have a balance condition, and those are what are called neutral solutions. So let's break that down a little bit more. The reference point is 1 times 10 to the negative 7 molar for an H plus ion concentration. This is what we call neutral. So if H plus equals OH minus equals 1 times 10 to the negative 7 molar, that's what we call neutral. And under those conditions, the pH is equal to 7.0. So let's take a closer look at the pH scale. We told you that a pH of 7 means that H plus equals 1 times 10 to the negative 7 molar. If the pH is less than 7, that means that we've got more than that. If the pH is greater than 7, that means we've got less H plus than that. So this is lots of H plus. This is a little H plus. Or lots of OH minus. Up here, this is little OH minus. pH is measured in what's called a logarithmic scale. And so the equation is that pH equals negative log of H plus. We'll be using this quite a bit in a second. Right? But do you notice that a pH of 7 meant that H plus was 1 times 10 to the negative 7? Right? So this is a logarithmic scale. It's on a power of 10, and 7 meant that the exponent was negative 7. Like I said, each power of 10 counts as a single unit on the pH scale. So if we have an H plus concentration of 1 times 10 to the negative 1, the pH is equal to 1. Or 1 times 10 to the negative 2, the pH is 2. I want you to ignore this one at the bottom of the screen here. We'll see what happens when we have things that aren't 1 up here. But if you have the power of 10, it will always correspond to a pH unit. So one more thing I'd like to take a look at, and it's sort of an imprecise way of measuring pH. For example, we can use pH meters, which are just little electrodes that we stick into a solution, and there's an electrical signal generated, and that electrical signal is related to the hydrogen ion concentration. We can also do it by color, which is sometimes more fun, and we have what are called these indicators. And the question I have up in the corner here is, what's a universal indicator? Well, we've got different types of indicators. The first one that I want to tell you about is what's not a universal indicator. This is a compound called phenolphthalein. Phenolphthalein actually you can find in some laxatives in the drugstore, but the really interesting thing about phenolphthalein is if you can buy it, you'll find that when you have a solution that has a pH higher than 8, so that's basic, right? Then I get pink. On the other hand, a pH with a solution that is less than 8, so acidic, neutral, and a little bit basic, you get colorless. But phenolphthalein only has 2 colors. It has pink or colorless. On the other hand, you can have different types of indicators like red cabbage juice, and this is something you can actually try at home. If you ever stop at the grocery store and buy a head of red cabbage, you can take a leaf off that cabbage and just boil it in some water and save the water, and then put the water in like a white Dixie cup or a clear cup or something like that. You just want to be able to see the colors. Then mix it with things from your kitchen. Mix it with lemon juice, or mix it with a little bit of salt, mix it with bleach, mix it with a bunch of things, and what you'll get is a whole bunch of different colors. Red cabbage juice is what's called a universal indicator. That red cabbage juice has a huge range of colors. Right down here at a pH of 1, it's kind of red. Up at a pH of 12, it's yellow. It can even go kind of like this greenish yellow when you mix it with bleach. I can really recommend it. It's a very fun thing to just try in your kitchen sometime if you're bored. And it's a universal indicator because it's got all sorts of different colors. You see how between 1 and 12, there's a really wide range of shades. And so indicators measure pH, but they're just not quite as precise. I can say, hey, the pH is between 6 and 7, but I can't say it's 6.5 like a pH meter might tell me.